Line emission spectra is proof that electrons exist at distinct energy levels called electron shells. If an atom containing several electrons is given sufficient energy, it will lose electrons. The first electron removed is the one with the highest energy. If more energy is supplied, it is possible to remove a second electron, and eventually a third, and so on. The successive energies required to remove electrons from an atom points to the presence of subshells within an electron shell. In this lesson, you will get to examine these subshells in terms of their relative energies as well as the shape and symmetry of the orbitals that are associated with them. Click on Activity 1 to begin the lesson. Electrons move rapidly around the nucleus in shells. Each shell can hold a maximum number of electrons. At the top left-hand corner is a box giving the names of the first 18 elements. Start with hydrogen and look at the number of electrons in its shell. Click on the other elements in the box, one at a time, until you finish with argon. What is the maximum number of electrons that can go into the first shell? Answer: 2. What is the maximum number of electrons that can go into the second shell? Answer: 8. The electron arrangement in argon is 2-8-8. The third shell can be expanded to hold 18 electrons. We can work out the maximum number of electrons each shell can hold by using the formula 2n², where n is the number of the shell. What is the maximum number of electrons the fourth shell can hold? Answer: 32. There are 3 shells shown which are numbered 1, 2, and 3. Click on 1. Now click on 2. Click on 3. Which of these shells has the lowest energy and which the highest energy? Answer: 1 is lowest and 3 is highest. There can be as many as 8 electrons in shell 2. The simple diagram suggests that all of these electrons are in equivalent positions. This is not so. Click on the line alongside the 2. You will see that the electrons can be in 2 subshells. What are these subshells called? Answer: 2s and 2p. What subshells are possible for shell 3? Click on the line alongside the tree. Answer: 3s, 3p, and 3d. The subshells are made up from different orbitals. These orbitals are represented as boxes in the diagram. Each orbital can hold a maximum of 2 electrons. An s subshell has only one orbital, which is called an s orbital. A p subshell has 3 orbitals and a d subshell has 5 orbitals. In shell 1, there is only one orbital. This is called the 1s orbital. In shell 2, there are 4 orbitals, one 2s orbital in the s subshell and 3 2p orbitals in the p subshell. 1 orbitals are available in shell 3 and shell 4. Answer: in shell 3, 1 3s, 3 3p and 5 3d orbitals. In shell 4, 1 4s orbital, 3 4p orbitals, 5 4d orbitals and 7 4f orbitals. Electrons fill the lowest energy orbitals first. This is in accordance with the Aufbau principle. Only when the 1s orbital is filled will the additional electrons start to go into the 2s orbital. When the 2s orbital is completely filled, the 2p orbitals start to fill. When filling electrons, you have to bear in mind the Polyexclusion Principle. An orbital cannot contain more than 2 electrons, and even then, only if they have opposite spins. Note that electrons can spin in 2 different directions, clockwise and anti-clockwise, as indicated by the arrows pointing in opposite directions. We are going to work out the electronic configuration in a lithium atom. A lithium atom has 3 electrons. Click on the box at the top left-hand corner. Click on Lithium. Click on Add Electron 3 times. You will see that the first 2 electrons are paired in the 1s orbital, and the third electron goes into the 2s orbital. The electronic configuration of a lithium atom is written as 1s2, 2s1. Click on Reset. Now repeat the process for neon. You will need to add 10 electrons. Check using the Am I Correct button. What is the electronic configuration of a neon atom? Answer: 1s2, 2s2, 2p6. The 3 2p orbitals are of the same energy. When these start to fill, electrons go into different orbitals with parallel spins. This is in accordance with Hund's rule, which states that when electrons are placed in a set of orbitals with equal energy, they spread out to maximize the number of unpaired electrons. Choose the element carbon. Carbon has 6 electrons. Add 6 electrons using the Add Electron button. The 1s and 2s orbitals are filled first. The remaining 2 electrons fill the 2p orbitals and they go into different 2p orbital. Now work out the electronic configuration of atoms of each element from hydrogen to argon. Check your answer each time. Can you get them all correct? Which element has atoms with an electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p5? Answer: chlorine. You will have seen the order in which orbitals are filled. Click on the Next Orbitals button several times to go through the order once again. Summary: electrons move around the nucleus in shells. Each shell can hold a maximum number of electrons. There are different subshells in each shell. Each subshell is made up from different orbitals. Electrons fill up the lowest energy orbitals first, Aufbau principle. Each orbital can hold a maximum of 2 electrons, Polyexclusion principle. Where there are different orbitals of the same energy, electrons go into different orbitals whenever possible, Hund's rule. Electrons are very small, are moving very quickly, and have wave-like properties. For these reasons, it is impossible to predict the exact position of an electron in an atom at any time. It is possible, however, to work out using quantum mechanics where electrons are most likely to be. The dots that appear represent the possible positions of an electron around the nucleus. This region in space where there is a high probability of finding electrons is called an orbital. You can see that the 1s orbital is spherical. Look at the 2s orbital. How is the 2s orbital similar to the 1s orbital, and how is it different? Answer: both 1s and 2s orbitals are spherical. The 2s orbital is much larger than the 1s orbital. What do you think a 3s orbital looks like? Answer: spherical and larger than a 2s orbital. Place your cursor over the structure and move the cursor to rotate the s orbital. What do you notice about the s orbital, whatever direction you view it? Answer: it looks the same from any direction. It is non-directional. Orbitals are often shown as solid shapes, and 1s and 2s orbitals are spherical. Use the Atomic Orbitals menu to select 2px. You will now see a dumbbell-shaped orbital pointing along the x-axis. This is called the 2px orbital. Now select the other two 2p orbitals, the 2py and 2pz orbitals. These three orbitals are directional. One points along the x-axis, one along the y-axis, and one along the z-axis. The three axes are at 90 degrees to each other. These three orbitals are said to be symmetrical about their own axis. What is the probability of finding a p electron at the nucleus? Answer: the probability is 0 or very low. Click on the 2p boundary surface. you will see the three 2p orbitals. What would you expect the 3p orbitals to look like? Answer: dumbbell-shaped like the 2p orbitals but larger in size. Use your cursor to rotate the p orbitals. Note that the p orbitals are symmetrical along their axis. Summary: an s orbital is spherical in shape. A 2s orbital is smaller than a 3s orbital. In the second shell, there are three 2p orbitals, all of the same energy, degenerate orbitals. A p orbital has a dumbbell shape. The px orbital points along the x-axis, the py orbital points along the y-axis, and the pz orbital points along the z-axis. The three axes are at right angles to each other. An s orbital is not directional, but a p orbital is.